question. So regarding the assignment that's due on Tuesday, I had a request to make it Wednesday. So I get it. I mean, you have an exam in heat and mass on that Tuesday. So I'm okay moving it, but here's the issue. The exam is, so the exam in this class is not the following Tuesday, but the Thursday after that. So I just looked it up and I posted the next assignment, assignment 5. You don't need to worry about it. I posted it just so that you could see it and be aware of it. At the moment, it is due the Tuesday, basically midnight, giving you just one day with the solutions before the exam. So I don't want to move that, okay? I don't want to discuss them in that because it's not in anybody's interest. I'll post the solutions. I'll have the solutions up at that time at midnight on Tuesday, so you'll have Wednesday to look at it before the exam. So here's the question. I don't mind being democratic. I'll go with majority rule here. If I move this assignment, it gives you less time for the next one. I'm happy to move that line because you have an exam in another class, but there's a consequence, which is that you have one less day for the next assignment. Now it's posted, which means you can get ahead on it if you're that kind of person. So the question is this: do you want me to move it one day later?
Yes.
With that consequence, understanding that I'm not going to move the next one.
Yes.
Okay, everybody knows the consequence. Okay, fine. Does it help? Do you want to do midnight on Wednesday or noon on Wednesday or 5 p.m. on Wednesday? Wait, did you hear me? I said I'm not moving the next one. So like.
It's not like we're going to start the same day. At like 5 p.m. It's not like we're going to start the next assignment at 5 p.m. that same day.
But noon.
I have a different when they're both
what time is the exam? Sunday, Saturday?
Okay. It's still done. Does everybody understand how this assignment's working? This next one? This is the only one that's going to work this way. Does everybody understand that you can hand it in groups? In the past, you won't be you won't think of this as a huge benefit, but trust me, it is. In the past, I had everybody work in groups and hand in individual assignments, and they had to be different, which was just a headache. So what I'm allowing you to do is hand them in groups for this particular assignment. There's a reason why I'm doing it. It's not because, oh yeah, groups, let's just have one assignment, we all work in groups. The reason is because this takes a lot of work of entering all this stuff. Use your groups wisely. If you put someone on your group who you think is just going to be dead weight, that just means there's more work for you, okay? The point of groups is because there's a lot of work to do here. I'm going to go through what it is now. When you pick your groups, pick people that are going to be successful at getting the job done, okay? Okay, I'm leaving it up to you. I used to assign them. Assigning groups is for freshman year, okay? You guys know who you are. You know who you like to work with. Be selective on who you work with. It's up to you. Does everybody understand how the Moodle thing works? There's actually groups in Moodle, and they have numbers. They're 1 through 20. Each number corresponds to one of the component pairs that's on the homework assignment. You could elect to be in a group or not. No more than 5 per group. There's 20 groups times 5. That means there's 100 people capacity. Okay? Take people into, contrary to what I just said, people need groups. Please put them in your groups because otherwise I need to have 30 groups and it's not going to work. Okay? You hand it in as a group. You get the grade as a group. Put your name on the assignment. Put all the names on the assignment so the TAs know who you give the credit to. Does this make sense? Okay? You will generate a lot of spreadsheets. Make it clear. Don't give the TA 100 sheets. They won't like it. Okay? Make it clear what the important stuff is. Okay? If you divide this up, it's easier than a single homework. That's where having like some level of teamwork management style comes in here. I'm not going to get into that. That's what I did in 110. Okay, we don't talk about that here. We don't need to. But divide the work up reasonably, and it's not that bad an assignment. But you have to divide it up and trust your teammates. If you don't trust them, it's useless. If you do it all yourself, this is a long assignment. Okay? So seriously, pick the people you want to work with well. The people who aren't here, don't work with them. Let them work with each other. Yes?
Do the TAs like grading an Excel or a PDF better?
You did I let you? I think I made it so you can hand in two. Hand in both. Okay? Hand in the PDF. But here's what I want. Make the PDF beautiful.
As presentable as.
Yeah, like imagine your boss is going to decide whether you're going to get a promotion or not based on the quality of the PDF. Did you think that I'm making that up? That happens all the time. Okay? So if it's I can't read it, it just doesn't even make the bar. Okay? This will be the answer is pretty short. You can get the whole answer for all three problems on maybe 2 pages. But the mechanics to make it all work, and that you need to show us that you work, is going to be more. So pull that stuff out, put it on the front, and then show this is how we did it deep into the PDF. And then that's easy, it's nice and clear.
Okay.
Does that make sense?
Yeah.
Okay. And also, so the thing that I dislike the most, and TAs dislike the most, is you make it a PDF and it breaks right down. You've got a bunch of columns you need to understand. You've got 3, 4, 5, 6, 7, 8, and it breaks. Squeeze it so that it fits, move it around so that it fits. It doesn't take that much time. It makes everybody so much happier. Okay, does that make sense?
Yeah.
Okay. Any questions on that? Any questions on Google Groups and all of that stuff? Okay? Yes?
What problem was graded in homework 2?
I don't remember.
Well, then I rescind my question for another day.
We'll have to ask the TAs to post it on the forum, okay? And then you'll know. They graded it and didn't tell you which problem they were grading?
Yeah. Oh, yeah, they graded it. Yeah.
Anyway, TAs are pretty good, so don't knock it. It's probably just a lapse, okay? All right, so last time I want to get through this. We have all the tools. We've missed one day because of those plans, and then we missed another day because of snow. So let's catch up as best we can. So we were talking about economics and design. And if you remember, we were trying to regenerate this graph, which had the dollar. We're trying to figure out how columns cost related to reflux ratio. And the equation that I put up at the end of last lecture was the cost of the shell was equal to some basis value. Don't worry about that for now. And you have this in your notes before. D over some basis, diameter, height over some height basis. These are all in tables to the AS, and these are all constants. These are all constants. And so this all is basically saying, if you know the diameter and the height, you can figure out the cost of a column. We have a similar one for the trays. But my point here is that now we're going to dive into 2 separate parts of today's lecture, figuring out the diameter and figuring out the height. Clearly the height is related to n, the number of stages, which is what we did before. Okay? So, I can give you this. Height is equal to height minimum plus height of a stage times n. Clearly. Okay, it's probably pretty easy. This is the space at the bottom of the column. All columns have space at the bottom. It's typically 3 times HT. Okay? HT is the tray spacing. And it's usually 12 to 24 inches. If it's not specified, you can use 24 inches. Meaning each tray is 2 feet. Okay? And then you know what that is. But there's one more thing that affects the height. Any idea? Obviously now you can go from N to H. You know how this makes a lot of sense. Obviously this isn't count right. It's a counting number, right? It's unitless. Now these are going to be in feet, and so now we're going to get an answer of height in feet or in inches. But there's one other thing that's being neglected here. It probably affects this. This might be a tricky question. See if anybody can get an idea. What else might affect the height? Let me see if I can phrase it this way. Are all columns? Now let's give the answer right. Do you think everything works perfectly? Do you think every one of these flash tanks is perfect? So how would you call that? Then you got a word for non-perfect. What's that word? Efficiency. Okay. So we're going to have something called stage efficiency. So why would it be a stage won't be efficient? Well, what does that mean in terms of what's actually happening? You have to kind of remember a little bit what I drew on the board over a week ago. But what does it mean if a stage isn't 100% efficient? In terms of like the whole thing, everything we're talking about in this course. Yeah?
If you were drawing the steps, you wouldn't be going straight and down.
It's not necessarily that it's not going up and down. You're on the right. You've got the right idea, but why? Why is it not going? It's not that it's not going up or down. Yes.
You're not achieving equilibrium.
You're not quite equilibrium. Okay. And what's causing that to happen? Why would you not be at equilibrium? What would cause something to not be at equilibrium? What's that?
Mist.
Mist is good actually because mist means you've got liquid at. We're going to talk. That's coming up in a few minutes. But mist actually is very, very small particles, right? So small particles have high surface area, which leads to equilibrium. But why? What's happening if you have a very, very small particle? What's that? Greater mass transfer. Okay. So if we don't get to equilibrium, it's because we have limited mass transfer. Okay, so we can actually do this way. We can say that the number of stages we need actually is equal to n theoretical over E naught. We could put a t here if we want, but now what I'm going to say is, just so you don't be confused, n theoretical is equal to the n which we had before, but it means we should revise this and put the actual there, right? So we're actually going to be costing this out. We need to take into account our efficiency. You can see this is just scaling our efficiency. And we can write an equation for E naught that looks like this. What do you think efficiency, I just told you it had to do with mass transfer. What do you think it's going to depend on? What do you think efficiency is going to depend on? Yeah?
Quality of your feedstock.
In what way?
If you,
You mean quality in the definition that we use, meaning how whether it's vapor or liquid?
well, not even that, just if you have more components going in, it's going to decrease how good the reaction is.
Well, it's not reaction, right? It's all physical. It's unclear actually how contaminants are going to affect it. Most contaminants are heavy, and they fall to the bottom. Not always, but most things are heavies. Asphalt, right? In petroleum refining. There's just stuff that comes out the bottom of oil. And whether it affects it, usually not that significant. It doesn't affect the volatility, but it does affect the very thing that I'm looking for the answer for. Think about asphalt. Asphalt's actually a good example. Why would it affect the efficiency? Because it is, yeah, go ahead.
Viscous.
Viscous. That's exactly what I'm looking for. So the viscosity matters. So it means that we can say that E naught minus A. Now A is just this is just an empirical term. So A is just a constant. 1 minus A is equal to the exponent minus square root of alpha. This is the alpha that we know and familiar with. This is our relative volatility. Question?
Yeah, just what is E naught again?
E naught's the efficiency.
Okay.
Oh, sorry. I'm sorry. Oops. Okay, so that's what we're looking for, right? You see, it just makes it so that our number of stages that we need is higher.
Okay.
If it's less than 1. Okay? Okay, where let me finish this? Over the viscosity over a viscosity standard. Okay? Where A is equal to, as I said, it's an empirical term, 0.24, and mu naught is 1 centipoise. What compound do you know well that has a viscosity of 1/10 poise? Thank you. I was expecting everybody, the chorus of that. Okay, so I guess fluid dynamics didn't drive that home. So everything's related to water, okay, and the relative volatility. Now, I want you to think about this for a second. Okay, this is it. This is the end of talking about height. Okay, we're going to move on to diameter soon, which is actually quite a lot more to talk about diameter. But let's think about this for just a second. Is there any opportunity here to manipulate and make it so that we can increase efficiency and decrease costs? Here's directly our cost term, because if our height is lower, the costs are less. If our efficiency is higher, our costs are less. So what do we want to do? Tell me a well-known dependency.
Well, the temperature.
The temperature. Now, here's the problem. Stay with, okay, we don't have to worry about efficiency with toluene benzene, but just do toluene benzene. Can I just arbitrarily, I want to give actual real binary pair. I don't want to think about A and B because you get confused. Benzene, toluene, can I just arbitrarily change the temperature? Why? Because the temperature is fixed by the pressure. Very good. Okay. So what do I have to do to change the temperature? In what way? Go ahead. I heard you say it over there. Say it.
Raise the pressure.
Raise the pressure. Okay. So what happens in a column? Remember, these are all VLEs up and down the column. As the pressure goes up, what happens to the temperatures in a column? These are all just VLEs stacked on top of each other. What happens to the temperatures? Temperatures go up. As temperature goes up, what does that do? Following this same train of thought. Viscosity is lower. As viscosity goes down, how does it change our critical parameter over there? Efficiency goes up. And what is the goal? I just erased it. Increasing efficiency allows us to do what?
Decrease costs.
Decrease the what?
Costs.
Decrease the cost. Yeah, okay, so let's just add a piece in here. So efficiency goes up, N and H go down, and then cost goes down. But there's a cost to this. What's the balance? What's the trade-off? Why don't we run everything at 1,000 atmospheres? If we can decrease the viscosity to increase our trade efficiency. Yes?
Energy?
Not quite. It was in last lecture. It does affect the energy, but that's not the thing I'm looking for. It's actually just a hidden thing, but think about it for a second. Why don't we run? Just think practically. Go ahead.
That's under high pressure, you need to make bigger plates.
Yeah, and so if you remember the cost term, the one that was right following this, there was a pressure term in there. What do you think happens to the cost of a column as the pressure gets higher? Yeah. I mean, you can think about this. I mean, this is a very practical thing. You have to make, your welding and how that thing's all put together. It's have to be much more higher precision in order to get to high pressures. The materials can't, at 1 atmosphere, you have to worry about it rupturing. But 1,000 atmospheres, that's a whole different beast. But can you see one reason why you might want to run a column at high pressure? Does this make sense? There could be a trade-off. Toluene benzene, our efficiency is probably very close to 1, so are you going to gain much by going to high pressure for toluene benzene? But if you have a highly viscous material, do you see the trade-off here? High pressure might get you past a high viscous material that's very far from efficient trade efficiencies. Make sense? Yes?
So if it's not very viscous, you wouldn't want to raise the temperature too much?
Wouldn't want to raise the pressure too much, yes.
Yeah,
Right. Which has the consequence of raising the temperature, you're right.
Yeah.
That's right. Because you might be close to 1 here, so there's nowhere to go. Okay, but if your efficiency is very low because your viscosity is high, right? Because this is going at the exponent of the minus square root of viscosity. Right? Your efficiency might get very small, in which case that's when you have that problem. Does that make sense? Okay, let's talk about weight. width or diameter. Now so far we haven't talked about width or diameter of columns at all. Everything has been reflux and number of stages. But what does the diameter of a column depend on? How wide does our column have to be? What's going to affect the width of that column? Think about it. I'm going to get into more details in a minute, okay? But just think about this for a second. What does that column width have to do? What's going on a width perspective in a column? Yes?
I mean, it deals with the amount of volume.
Yeah, the volume, or not necessarily volume, but you've got the right thing, but it's not quite volume. There's a part of that term missing. It's the, yes?
Surface area?
No, he was close there before. Volume of what? Yeah? Correct?
The weight of the fluid.
The weight of the fluid, which is going to be given by the, I'm just looking for it, it's close to volume. The weight of the fluid is, we're going to get there, you're right on it. Density, no, but like it's, if I have a lot of volume at a short amount of time versus a lot of volume over a long period of time, flow rate, okay? So it's the flow rate. So it's volume, but the flow rate, okay? But what affects the flow rates inside the column? There's the feed flow rate, but what affects those internal flow rates? Do you remember what had a big effect in a very kind of obvious way? On those, yes? The reflux ratio. Okay, so we have the feed flow rate and the reflux ratio, and those affect the internal flows. So now the question is, how does that, if we know the internal flows, how do we figure out what size column we should have? Okay, so a column of a given size can only operate within a limited window of flow rates. So if we look at, now what things are flowing through a column? Do you remember my picture that I had last time? I'll just do a little one again. Remember that picture? What things are flowing through a column? Yeah.
Vapor and liquid.
Vapor and liquid. So we have a vapor flow rate. And this is conceptual, this picture, so I'm not going to put units on it, but this is low vapor flow rates and high vapor flow rates. All proportional to the components and the column that you're looking at. Okay, so in the center, you have some kind of shape like this, where it's stable, where everything works. We have a region where we have flooding, a region where we have entrainment, and a region where we have weeping. Okay? Some of those words, so this is kind of like the flooding region is over here, the entrainment region is over there. Most of what we're going to do, we're going to be interested in is flooding. Okay? But I want you to think about these conceptually. Just think about how this thing's working. So what happens when my vapor flow rate is high? So this is not working. These columns don't work. in any of these outside regions, they only work here. Okay? So let's just talk about, say, entrainment first. We have a really high vapor flow rate and a low liquid flow rate. What's happening there? This, I think, one of you actually gave me, you were talking about this already earlier. I might not have known that it was called entrainment. So we have the vapor is really high, but the liquid is low. What do you think is going to happen in that column? Go ahead. Think this.
Correspond to maybe boiling azeotrope.
There's no azeotropes. Just think benzene toluene for now. Just keep things simple. Just VLE in each of the stages. Yes.
The liquid product is probably going to be very pure, but the vapor product will not be.
So think about it on a stage-by-stage basis. What's happening in here? You get impurity in both products. Wait, so you said the liquid will be pure, but the vapor's not? Yeah, that's basically what's happening. Why? What's happening? You got the right idea, I think.
Well, you can assume that the lower boiling point component is going to be all vapor because it's mostly vapor, and then the whatever is left in the liquid is going to be the higher boiling point composition.
No, that's not quite what I was saying. But think about what's happening here. Remember, this is all a big frothy thing. Go ahead.
The vapors, like going through the stages too fast that it's not reaching equilibrium.
Yes, it's not reaching equilibrium, but actually it's not reaching equilibrium, not because it's actually more chaotic than that. It's not that it's going too fast. If it goes too fast, what do you think it might do? I'll tell you if it's not obvious. Yeah?
Like run out of liquid.
No, it's even more dramatic than that. Yeah?
It's like pushing all the liquid out of the way.
It pushes the liquid up to the next stage. Okay, so it's taking the water droplets with it, and therefore you're not getting to equilibrium. So it's taking this liquid up to that stage. Okay, I'll write that down. So it's incomplete separation. Okay, entrainment. You can imagine that, right? There's lots of froth and foam here, and the vapor is so fast, instead of just having a VLE here, it's just taking the liquid from one stage up to the one above. So that's entrainment, when you have very fast vapors. Okay? So what will happen is, it'll just seem like your efficiency is going to be very, very low. So it just won't look like it won't work. What do you think flooding is? Flooding is not as dramatic. Flooding is you have high vapor rates and medium liquid flow rates. And flooding is what we're going to look at for sizing our columns. What do you think flooding is? It's not as dramatic as entrainment. Entrainment just looks like a column doesn't work. But flooding is a slightly more subtle problem. What's making that thing work? Which way does liquid flow? Which way does the vapors flow? And do we need to pump any of that? No. So what's happening? Okay, flooding is kind of the opposite of weeping. Okay, maybe think of it this way. What's weeping? You kind of imagine this, right? Remember, this is just a sieve. This is just a grate. Why doesn't all the liquid just go right down to the bottom of the column? Go ahead. What is it? The vapor pushes it up. So what happens when we have a low vapor flow rate? The liquid falls down. Okay? And then are you getting separation when you're weeping? You're not near equilibrium either, okay? Liquid flows through tray openings, okay? Rather than downcomer. Okay, so that's weeping. What's the opposite? Instead of having too low a vapor flow rate, so the liquid's all falling down, what do you think flooding is? Now we have a too high a vapor flow rate, and what's happening then? Yeah, go ahead. Yes?
The vapor is like boiling over the liquid.
It's not quite that it's boiling it over, yeah?
Would it be pushing the liquid up over?
Okay, you guys all basically have the right idea. It's not letting the liquid fall down.
Yeah.
Okay? It's holding the liquid up on the stages. The liquid, what makes this liquid fall down? What makes it fall down? Gravity. That's right. Right? And what force is pushing it up? It is the vapor, but what do you call that? It's not quite buoyancy, it's, right? Because the buoyancy is actually making the liquid fall. What's holding the liquid up? It's the kinetic energy, right? It's like the flow rate of that vapor. Anyway, does that kind of make sense? That you're balancing like the drag. So if the drag of the vapor is too high, it's holding that liquid up and not letting it fall down due to gravity. Does that kind of make sense? Anyway, at the moment you need to know that it's a drag between the phases is greater than gravitation. So flooding is kind of, in some ways, the opposite of what you think. It's not flooding like down the bottom of the column. It's flooding the top of the column. So you have too much liquid at the top of the column. Okay. Okay. So like I said, we're going to use flooding to help size our column. Why is that? What's going to affect? How is the size or the diameter of the column going to affect whether it floods or not? Before I do all the math, and the math can get a little bit, I'm going to go through it, it's going to have somewhat level of complexity, and it's going to all simplify like it often does in this course. But why is the diameter, so we're going to think about this conceptually before we get any farther, going to affect whether the column floods or not? What does the diameter change? Yes?
The size of the tray, so it can be bigger and hold more liquid, so it won't flow over.
It's not about the liquid, it's about what's changing, what's important there, for it to flood. It's not the liquid flow rate, the vapor flow rate. So how does the diameter affect the vapor flow rate?
If you have a smaller area, you have more pressure pushing out.
It's pressure, but think of it this way. If we have a set flow rate, oh, I just erased it, and I change the diameter, what changes? I have a set flow rate of vapor, and I make the diameter smaller. What increases?
Velocity.
The velocity. Okay? So as I increase the velocity, what now increases in my column?
Liquid at the top.
The drag, right? So as I get smaller and smaller, do I get more and more force holding that up because I now have a higher velocity? As I make it wider for the same flow rate, okay, same flow rate, what's happening to the velocity as I increase the diameter? It's lower, so then the liquid can now fall, and at some point you get weeping. But what you want it to do is you want it to be just enough that you sit in this space. Does that make sense? So what we're going to do is we're going to size our diameter such that we're here and we don't flood. Does that make sense? Make sense? Okay. So we're going to design the column to be in the stable region. This is dictated by vapor flow rate. Or more specifically, that's what we just talked about. Molecular flow rate, it's the superficial vapor velocity. Which is defined as U, vapor flow rate, the molecular weight of the vapor, divided by the density of the vapor. Remember, all of our velocity, all of our flow rates at the moment are in moles, right? All of our problems have been in moles. So these two terms, these are just conversions. This is just making it from moles into mass and mass into volume. Okay, so this is just going from a flow rate which we think about in moles, we're very used to moles, to a flow rate in liters, which is something we're also used to. It's just a conversion. That's all that is. Divided by the cross-sectional area. Okay, there's nothing fancy happening there. These are just terms that we're used to. This is molecular weight and density. Okay, nothing strange. But do you see where the diameter comes in? There's the cross-sectional area. So as the area gets bigger, the velocity gets smaller. And as the area gets smaller, the velocity gets bigger. Just what we just talked about. That's intuitive. Okay? Okay, so now I'm going to show you a bunch of empirical correlations to help you figure out, find the flooding limit. So the flooding limit, I remember I told you this is going to be, I'm going to show you a slightly more complicated version, and then it simplifies in a bunch of cases. So the flooding limit is dependent on the kinetic energy of the vapor. Rho u squared. Okay? We're going to represent this with an F factor. And again, this will simplify. And it's empirical. So it's not like thermo, where there's a lot of first principles. There's a couple of first principle components here, but a lot of this is empirical. Okay, so we're going to have an F factor, which looks like this. F is equal to u square root of density v. You can see it's just derived from that kinetic energy term. So we rearrange for A. So in other words, we're going to solve this for A and use that F factor. We find that A molecular weight over F square root of density times V. That's equation 1. Okay, so we can always find the area if we know the velocity V and that F factor, the point at which it floods. So we're going to find some F when it floods. Again, it's empirical. And then we can find from the velocity, from our flow rate, our cross-sectional area. The F factor at flooding is given by this. F flood is equal to, remember this is mostly empirical, A over AN over A. This is just a constant. I'll get to this in a second. AN is I'm going to erase my picture. So if you look at the cross-sectional area of a stage, the total area is A. AN is the area minus the downcomer. Okay, so it's the area at which you have vapor flow. Okay, I'll define that. Don't worry about it. Then it's dependent on the surface tension over standard. Notice the empiricism, 0.2. The difference in the liquid and vapor densities, where C is the capacity parameter. I'll get to that. AN is a net area for flow. Which is typically 0.8 of A. So the space left for the downcomer is 20% of the area. That's all that says. And the area of the of the sieve part of the tray is about 80%. That's all that is. The capacity per, oh, hang on, let's do the, so this is the surface tension. And sigma naught is 20 millinewtons per meter. Okay, the capacity parameter is given by this equation. C is equal to C naught over 1 plus C1 F to the C2, where C1, C0, C1, and C2 are in table 6.1, and they're constants. Where F is the flow parameter, bear with me. I'll simplify all of this, and the simplification is the key. Let me put equation 2, equation 3, equation 4. Okay, so that's the average liquid density and the so rho L is the average liquid density, and rho V is the average vapor density. How do you get rho V? How do you get the density of the vapor? What's the easiest way to get the density of the vapor? What is it? Ideal gas. Okay. So to calculate A, first calculate L and V from R and S. Reflux ratio, reboil ratio, right? We all know how to get the liquid vapor flow rate to the column from R and S. 2, estimate the density of the vapor. I'm sorry, the molecular weight of the vapor, the molecular weight of the liquid, the density of the vapor, and the density of the liquid. So then you do 3 is find F using equation 4. 4 is find C from 3. 5 is calculate F flood from 2. And finally, so then we're going to set F, this is step 6, is equal to 0.6 F flood. Now why am I doing that? I want to make sure this is clear. So if the point at which it floods is F, think about the diagram which I've erased. Here's flooding. And this F that we're going to calculate is the point at which it floods. Why do we want to set F that we're going to actually design by 0.6 of that? Go ahead. Yes, okay. But I get this question every year. Someone asks me, why 0.6? I don't know, it works well. Okay? The heuristic is, if you go very much lower, you get weeping. Okay? So how about if we just go 0.6? And this is not talked about that much, but this is engineering. We can figure out where this line is. We know we don't want to be there, so how about just 60% of it? If you design the column and it doesn't work, will you adjust it? Yes, but is that a reasonable place to start? Yeah, it's reasonable. Is there any real theory behind that? No. Do you want to build a column here? what's happening to the size? As we go more towards flooding, is it getting smaller or bigger? Smaller. So what's the fear? If you build it here, you built too small of a column. And if you have too small of a column, what's that going to do to your total throughput of the column in the end? It's going to decrease it if it floods. You can't make as much stuff. So the downside of having it be too big is you have to make more, which is not as big a problem as having too small. Does that make sense? So 0.6. But this is engineering. This is where it's different than science. Why 0.6? Because for the most part that works. Does that make sense? Like why when they build a bridge do they say, figure out the strength you need, double it and double it again? Why? Because then you know it's not going to break. But why does that work? I don't know. This works. Okay? Does that make sense? So in other words, this is experience. That 0.6, it's experience. Other engineers have found that works. Right? It may not work for every column you build, but it's a good stuff. Okay? Then finally, step 7, if you know F, you plug it into here and you calculate A. Am I fair in saying that if you remember my equation for cost way at the beginning of this lecture? It didn't have A in it, it did it in terms of what? Diameter, right? Can you all convert from area to diameter? Everybody should nod, yes. Okay. Don't forget to convert from area to diameter. If you're doing this really fast on an exam, what will you forget? You have to convert from area to diameter. Why will you forget that? It's because you won't keep track of your units all the way through. Whereas if you see this has areas of meters squared, you'll know you don't have to figure it into meters in order to be correct. But this is why units matter. If you keep your units through this, it'll make it easier. Now, I promised you a simple version. Let me give it to you. This is the more complicated version. If you can star that if you like. Simplification. If the density of the liquid is much, much more than the density of the vapor, how often does that happen? Often. Okay? And the sigma is about sigma naught. So the surface tension is similar to the surface tension of water. Is that reasonable for a lot of things? It's reasonable. Okay? There are things that won't work or it won't work for. Okay? But if this is the case and this is the case, then F flood is given by square root of the density of the liquid AN over A times C naught. This term doesn't end up mattering. And A is given by the molecular weight of the vapor over the square root of the vapor times density of the vapor, density of the liquid. 1 over, and I'll define this term, it's just 0.6. Okay, let me just write this down here. It's this number right here. It's what percentage of the flood are you going to do? It's that 60%. Times C naught, this is a single number. It's 439 meters per hour, I believe. Anyway, you'll find it's just a constant. You look it up. A over AN. What's A over AN? Oh, actually, what's AN over A? I told you. Typically, it's 0.8. So AN over A. So this is 1 over 0.8 times V. Okay? And that's a number, that's a number, that's a number. Those are densities you estimate in the molecular weight. Has this gotten a lot easier? It's still a complicated looking equation, and I don't expect you to memorize it. That's why it's open book. But is this, does this make sense? That your area is related to your vapor flow rate with a conversion between molecular weight and density, and some ratio of flooding? Does that make sense? Roughly? You have to understand that it's not the point of this. It's empirical. But this is kind of, could you do this? Okay. Know how to do this when these approximations aren't true. These two both have to be satisfied for this to be true. Okay? None of this is that much harder. It's just 4 more steps of algebra. It's just plug and chug. This does the same thing. It's just a little quicker. Yes? Yeah, go ahead. Which equation are you looking at? On this side here? Phi flood. Phi flood. And phi flood is equal to 0.6 most of the time. It's just the ratio. What's F flood over F? What do you want F to be? 60%? of Fy. Okay? Oh, I wrote this down. So C naught for a 24-inch tray spacing is, and I was right, 439 meters per hour. Now, when you do this in your homework, this is where the spreadsheets get a little tricky. Units are very important. So when you do your spreadsheets, keep track of every value in units, because notice that we're going between meters and inches, back and forth, in a very confusing way, which only engineers do. Okay? We can complain about it, but until you can get the manufacturers in this country to sell everything in metric, we're going to have that problem, because all scientists do everything in metric, and all manufacturers do things in feet and inches. Okay? That's why tray spacing is in inches, because you buy columns in feet. Okay? But all of the thermodynamics is all in centimeters and SI. Okay? So the person who has to integrate it is you. Okay? But that's what they pay you the money for. Yes?
There isn't a program that switches units for you, right?
You know, in Excel, it's a box, and you put a number in. It's 2.54, right?
I didn't say it.
No. What I'm saying is it's not that hard, okay? Just keep track of yeah. What? Good question. This is the ratio of A to AN. Yeah, I get that's a question I get before. This is just 0.8, right? This is the ratio of the two.
Oh, okay.
Right? So it actually kind of cancels out here. This is the ratio of exchange area over the whole area. So this is always just going to be a unitless number.
Oh, okay.
It always is A over A, AN over A. And I know it's you can divide it out and then it makes no sense, but just don't divide it out.
No, I missed that note.
Oh, yeah, what you could do is if you divide this, you'd still be solving for AN.
Okay.
And then you have to multiply by 0.8 anyway. So, does that make sense?
Yeah.
Yeah. Go ahead.
That ratio would be 1 over 0.8.
This one is 0.8. This is 1 over 0.8. Okay? It's inverted in here, okay? I'm pretty sure I have that correct. Okay, you might want to check it. I think it's this way up in this one and inverted in that one. Okay? I'm pretty sure, just check it, okay?
No, you're right.
Okay. Any questions on flooding and diameter? Does this, now, here I end and all of a sudden it's like, wait. Do you understand that this is an important part of the costing? Do you see what it's making it dependent on? The important term here, all of this conversion is somewhat superfluous. This is what matters, right? It's that the diameter is dependent on the vapor flow rate. And the vapor flow rate is dependent on two important things. We did this at the very beginning. It's dependent on the feed flow rate and the reflux ratio. Okay? So that's why R matters, because it affects the diameter of the column. One last thing, you will see columns built this way, where the bottom half will have a different diameter than the top. Can you imagine why that would happen? Can you see why you might get different vapor flow rates in the bottom and top of a column? We had columns like that. Okay, so just something to think about. Here, V is left without a subscript. But remember we have a V top and a V bottom? If they're dramatically different, such that one is flooding and one is weeping, you need to have different widths of the column. If they're close to each other, it's probably cheaper just to buy a single diameter column. But if you go look around, you'll see, if you type in distillation column into Google, you'll get pictures of them. You'll see ones with different, with like a shoulder halfway up, where the feed is. Okay? Because of this, you have different feed vapor flow rates at the top and the bottom. Okay? For the most part, you can keep them the same. Does that make sense? Okay. Something to think about. Am I okay moving on from diameter and vapor flow rate? Yeah? Okay. So what were the other things? So now we've got, in my term, we now know the height and diameter, so we can cost out our trays and our shell, right? But there's one more piece of equipment, or now we've got the whole main column costed. What's the other thing we need to figure out? The cost of? The heat exchangers. Right, exactly. exchangers is the condenser. And reboiler. So for a lot of columns, a lot of alkanes and alcohols that we use as examples in this course, it's not true for everything, but a lot of things that we can use, you can actually, they boil lower than water, and they and the lower boiling point is lower than cool water, so you can actually use cooling water for the condenser and steam or superheated steam for the reboiler. And those are very cheap utilities, right? If you think about it, UMass has a cooling water facility and a steam facility. It's just a lot of places. This is a chemical plant, right? So steam and hot water and cool water are common. Not everything, of course, has boiling points between cool water and steam, but they work fine for a lot of pairs. So that's what I'm going to show you here. Of course, if you have to heat something higher than a steam, you can use electricity. There's many things to use for heating sources. And similarly, if you've got a cool lower than cool water, you can use refrigeration. But of course, that's more expensive, right? Obviously. Okay. So if we're going to use steam, we're going to use cool water for this, and steam here. There are two things that are going to affect the costs. And it's actually the same for both, okay? But how are the costs of my column going to be affected by a cool water condenser or a high-pressure steam reboiler? What's going to affect the cost? There's two things I have to take into account. I need to know two answers.
Insulation.
Let's assume for now that it's adiabatic, just so that my life's easier. Is true adiabatic possible? No, but let's keep it nicely insulated, and that's a secondary thing, and important, but I'm going to go simple. Okay? What else? Something simpler than that. I need to know. Go ahead. Oh, you make it even simpler than that. You're right, of course. I'm going to talk about it, but just, yeah.
The temperature of the steam.
Temperature of the steam, even easier than, well, not easier than that, but what is that? What am I trying to figure out? In terms of, I need the cost. I need to know how much it's going to cost to, that's it. What's the answer? I heard it. You said it. Heat it. Someone said how much, right? That's what I need to know. What's the flow rate? I need the flow rate of cooling water. I need the flow rate of steam. What else? So I need the flow rates of both of those. And that's, of course, going to have to do with the enthalpy and the temperature. Okay, we'll get there. And one other thing. What else is going to affect the cost? It's very different than the flow rate. What other thing do you have to do? Same thing that we did with the column. We need to buy the thing. What do I need to know? Yeah. The area of the heat exchanger. Basically the size of the thing, right? So we need to know the size. Or the cross-sectional area of heat exchange, okay? So both of these are dependent on the heat requirements. Okay, and if you remember, QC is given by lambda R plus 1D. Go back in your notes so you can find that. QR is given by lambda SB. So we know we can find both of those dependent on S and R. B and D are dependent on our purities. Okay, so we have those. All right, let's do this. So this is all of heat transfer summed up in 15 minutes. Okay? This is the same L1 that we had before. This is our reboiler. So we have L1 coming in. We have V0 coming out, and our bottoms product coming out here. We're going to have a countercurrent heat exchanger, so we're going to have steam coming in, and we're going to have steam coming out. Okay? We're going to have the temperature of the, hang on, let's not do that yet. Those are good questions. Then we have a condenser. Similar. Where we have Vn, the same Vn that we're used to, and before we split it, we now have Ln plus 1 plus D coming out there. So now we have cooling water coming in here. We have cooling water coming out here. Do you know this temperature? Do you know the temperature in the, I'll call it the flash side or the component side of the heat boiler? What's the temperature? I'm not saying what is it. I don't want a number. You're not going to know the number. But can you find it? Go ahead. It's close to the point. It depends on the purity, right? If you had a low purity bottoms, but can you find the boiling point? I mean, can you find the temperature there? It's just given by the temperature at that equilibrium. Okay, which is, if you're very, very pure, it's the same as of the heavy component. Sorry, yes. Okay, but let's just say this is the temperature of the bottoms. This is the temperature at which equilibrium happens at the bottom. What about here? What's the temperature on the component side in the condenser? We do the same thing. Do the same thing. What about the steam? What is the temperature of steam dependent on? Remember here, this is from probably thermal 1, not thermal 2. Did you do steam tables in thermal 1? Or do you in thermal 2? Yeah? Depends on the pressure, but at a given pressure, what's the temperature of steam? Does it change? No, it's a fixed temperature. And yes, you can adjust it by changing the pressure, but at a given pressure, it's a single temperature. Temperature of the steam. Here's the trick question. What's the temperature here? What's the temperature in the cooling water side of the condenser? This is unique to cooling water, but if you use cooling water, yeah?
Would it vary?
It varies. That's the answer. I'll make the rest up. So, and it gets, as it goes here, what's happening to it?
Heating up.
It's heating up. That's the answer. I know that sounds like that's not very satisfying, but cooling water, this is constant across the whole heat exchanger. This temperature of the steam doesn't change. Because what's providing heat to the reboiler if you're using steam? It's not enthalpy, well, it is enthalpy, but it's what's happening. If you put steam into a heat exchanger, what gives you the heat? If you keep it at constant pressure. It's a simple thing, we talk about it all the time. It's actually written on the board in one way or another, yes? It condenses, and so what's the heat? What's the name for that? It's the enthalpy of vaporization or the latent heat. Same thing. Okay? So the latent heat of the steam is what causes this to heat. So what's happening is we're going to get water coming out, and that's what's causing that to heat. Does that make sense? That's how you use steam. But the temperature is not changing because we've got a two-phase system here. For the same reason that the temperature is not changing here because we have how many phases? 2 phases. Okay? And again, we have vapor coming in, liquid coming out. It's all condensing, but it's 2 phases, so it's all at one temperature. But what's happening here? How many phases in this one? In the cooling water? Just 1. All right? So here we're talking about heat capacity. Right? The water is heating from T cooling water in to T cooling water out. Okay? So we have to be a little more tricky about how we handle the cooling water. Okay. Flow rate of steam. So the flow rate of steam is given by the this QR, oops, sorry. The heat required of the over the change in enthalpy of the steam. I can just replace that over there, and I get lambda over delta HST, change of enthalpy of the steam, times, sorry, ST. And I know this might sound unsatisfactory, but this value, the enthalpy of the steam you can get is given in a table in the book, and it gives you a cost per kilogram. Okay, so if you look up table 6.5, you pick a temperature above your temperature of your bottoms. Okay, so just pick any temperature above, and it gives you in kilojoules per kilogram, and finally gives you a cost in dollars per kilogram. Right? So you're going to get this value in kilograms, in kilojoules per kilogram. You're going to know the kilojoules. It will give you a kilogram, and so then it's going to give you dollars per kilogram. And it's actually it's just a conversion. Okay? So that tells you if you know how much heat you need, you're just going to be able to get a dollar value for the steam, as long as you pick a reasonable temperature. Okay? For cooling water, a similar conversion for cooling water. So to go from 30 degrees to 50 degrees C, it's $0.0246 per thousand kilogram. Okay? So what's the energy required? How do I know how many kilograms of water I need to put in here? What gives the energy to go from the cooling water in to cooling temperature, cooling water in to cooling water out? I should kind of give the answer already to this. Yeah? Okay?
The heat capacity.
The heat capacity. Okay? So the energy required is given by Cp delta T, where delta T is equal to T cooling water in minus T cooling water out. And you could just use those values, as long as that's cooler than the temperature you're trying to get to, your temperature of the distillate. And then the flow rate of the cooling water is just given by this. Flow rate of the cooling water is given by QC over Cp delta T. Okay? This is the energy required. This is going to give you energy per kilogram, Canadian kilograms of energy required. So I just erased it. All right? Does that make sense? And so then if you know kilograms per time, you can now put in kilograms per time, and you get dollars per time. Finally, what about the size? What dictates the size of a heat exchanger? Can I erase this part for the reboiler for now? Can I erase this right side? I'll leave the cooling water up for a second. Any problems with that? I just said the size. So what dictates the size? Does anybody remember the equation for that? So here we had Q equals Cp delta T. Okay, that's how much energy it takes to heat this water up from one temperature to another, from 30 to 50 degrees. Okay, that's Q equals Cp delta T. What's the other one? Where's the heat exchange that is actually doing the work that's going to define this heat exchanger? You know the other equation for heat exchanger? Anybody know it? So this is Q equals Cp delta T. What's the other one? Where's the heat? Just first tell me where the heat exchange is in that I'm interested in terms of sizing this heat exchanger. Does anybody know what these look like? I've drawn these like boxes, but what does the heat exchanger look like? Tubes inside a tube, right? Of all different shapes. There's a tube inside a tube where these don't touch. Well, what's important about that? What's the important parameter? That's right, surface area. And what's the parameter that affects the heat exchanged across that surface area? Anybody know? Everybody know the equation? Heat transfer coefficient? Nobody remembers? Q equals UA delta T. Have you had that yet?
Just.
So you couldn't remember, okay. Anyway, so Q equals UA delta T. What's U? Well, U depends on what in this heat exchanger? What does U depend on?
Material.
The material. Oops, it's usually written without a tail for some reason. So this is the heat transfer coefficient. And it depends on the material. There are a whole bunch of materials listed and their heat transfer coefficients, again, in the book. Now, what's delta T for the reboiler? What's delta T for the reboiler? This is the easy one.
0.
Someone tell me what the delta T for the reboiler is. What's the high temperature? Which one's higher? T-steam, okay? And which one's lower? TB. Okay? So, these are numbers you already basically know. You look this one up, that one you know. All you need to know is U. What's Q in this equation? That's U. What's Q?
Heat.
Which heat? Let's say that loud, you're right. Heat of the reboiler, so it's QR. The same QR that we had, I just erased it, okay? So this is QR equals UA delta T, you look up U, and that allows you to calculate A. And from that area, you can calculate the size of the heat exchanger. But which one's harder? Where does this equation get more tricky? Why is it trickier for the condenser? What's the difficulty? It's almost exactly the same thing with one difficulty.
You don't know the temperatures.
You don't know, well, it's not that you don't know the temperatures. Where's the temperature of heat exchange? It's from TD to, how would you do it in heat transfer? If you were going to do it carefully, is the heat transfer, the rate of heat, the amount of heat that goes across at this part of the heat exchanger different than this part? Okay? Whereas here, Q is constant all the way across, right? That's why we could just use that simple average Q equals UA delta T. So what would you have to do if you would be really careful about this in heat transfer? You'd have to integrate across the whole length, okay? But there's an approximation, which I don't know whether they'll teach you in, you have Dan hour for that?
Yeah.
I don't know if they'll teach you this approximation, but there's an approximation called the log mean temperature difference. Which approximates that integration, and it's this. The delta T average is equal to TD minus T cooling water out minus TD minus T cooling water in. Again, this is just 30, 50, and TD you know, okay? So this isn't tricky. Natural log of TD minus T cooling water out over TD minus T cooling water in. Notice it's all in, out, and TD, okay? It just gives you this average difference. You then plug that delta T into here. You look up the material, you know, the heat transfer coefficient. You know QC, and therefore you can find A. Does that make sense? And so then the cost of a heat exchanger, I'll give you this last part. Can I erase this? I can erase this now. You get a similar equation where the cost of the heat exchanger is given by, this is like what we had before, some basic cost of the heat exchanger, A over A naught, where A is our area, to be AH, where AH is equal to 0.65, COH is given by this Marshall and Swift, Marshall and Swift base. FD plus FP. FM. This is material. This is type pressure material. Minus 1 plus Fi. FD. These are all numbers you just look up. Times COH. This is the 1970 cost. This is the type, pressure. These are just the things you look up. This is material. This is an indirect and a direct factor. And then let me give you the one last thing. At the moment we have two things. We have a capital cost and an indirect cost. This is the last piece. I'm running out of time, so I'm just going to present it without talking about too much. To sum this all up, because we're going to do capital and operating differently. So do it the way it does it in the book. And you're going to get this thing called total annual cost. And it's just this. TAC, again, this is entirely empirical, is equal to 2.43 K cap plus 0.19 C capital plus C operating. And this just allows you to put operating and capital into the same equation. And K cap is the capital charge factor. And it goes from 1/3 to 1/4 per year. Okay? So what this does is this gives you a final scalar. The cost of the columns, the trays, and the heat exchangers goes into C cap. The operating costs is the cost of water and steam. You put these into this equation, you get a final dollar amount, and it allows you then to compare whole systems by changing R. You see how that's going to work? Calculate R, calculate N. Now you know N and R. You're then going to be able to, from R and N, get the size, diameter, the size of the column, the size of the stage, the size of the heat exchangers, the amount of water and steam, and you get it all back to a single number. Yes?
I just want to clear about what you wrote under K cap capital charge factor.
It's 1/3 to 1/4 per year. Sorry, I'm running over on it, but you need is the last piece you need for the homework. So 1/3 to 1/4. Yes. Sorry. That was a good one to look up in the book anyway, because all those parameters are just in the book. So I just wanted it in the notes so you can see how everything tied together.